Okay, so we looked at the second derivative before the break, right? And the second derivative kind of tells us two things, right? Let's warm up by writing that over here. So for a function f double prime does what? Tells us what? Yeah, f double prime number one, it tells us the concavity. Concavity. What's another name for concavity here? Curvature, yeah. Tells us the concavity or the curvature of f. Okay, tells us the curvature of f. That would be analogous if f was analogous to your position function, just to kind of bring it back to particle motion. This would tell us the acceleration, right? Something like that. But remember, it also tells you something about f prime. It tells us if f prime is increasing or decreasing, which would be analogous to velocity increasing or decreasing. So it tells us two things. All right, it tells us about f, about the curvature, concave up, concave down, but it also tells us if the derivative, if the slopes are increasing or decreasing. Okay, so keep that in mind. All right, so what we're going to do now, oh, and by the way, remember, this because it's been 9 days, if we know then the sign of both the first and the second derivative on any given interval that's continuous, we know it's going to look like one of those parts of a circle. If we then combine the function values with that, we know then where to put those pieces right there. So what we're working towards is how can we judiciously sketch a graph of an unknown function f by not having to just make a random chart and plug in and get values and then connect the dots, okay? Because then we can use those points then for applications for mathematical models. Okay, so let's go ahead and we might have defined this before the break, but it's worth doing again. All right, so a possible inflection value, what I label a PIV, a possible inflection value of some function f, is an x value that's first of all in the domain of some function f. So the function is defined there. Doesn't have to be continuous there, but it does have to be in the domain such that one of two things happens. Either the second derivative is 0 or the second derivative is dne. Okay? Those are possible inflection values. So let's go ahead and say this. This is an analogy. So f prime is to critical values. F prime is to critical values as f double prime is to possible inflection values, PIVs. Okay, and of course those are CVs. Because remember, that's how we found critical values. We looked to see, first of all, where the first derivative was 0 or undefined, and if that value was in the domain of the function, it was a critical value. Now remember, critical values are possible local max or min locations, right? Possible local max or min locations. There is no other term for a possible inflection value other than a PIV, but PIVs are then possible inflection values where the graph actually changes its curvature. So we can't say that every critical value is a local max or local min, and we can't say every possible inflection value is an actual inflection value, okay? But it's a possible location. So let's talk about where a graph can change its concavity. Let's come back up here. Notice we said that at x equals p, the graph changes from concave down like a frown to concave up like a cup. That means the sign of the second derivative changes from positive to negative. Well, through a continuum, if you go from a positive number to a negative number, what number do you have to pass through? 0. So right there at that point, the second derivative at p is equal to 0. So by definition, we would say that that's a possible inflection value. Now, does it actually end up being an inflection value? Yes, because the sign of the second derivative changes. Okay? Yeah. Oh no, I did that. Those are both backwards. I'm glad we revisited that. Yeah. That was like right before break, and I think in my mind I was already on break. That's less than 0, and that's greater than 0. Thank you. Thank you, Jack. Yeah, okay, so if you're watching that old video like this guy has no idea what he's talking about, at least Jack does, right? There you go. That's negative, concave down like frown. Yeah, let's even go back further, right? Concave down like frown. Negative second derivative, concave down like frown. So any part of a frown, positive second derivative, concave up like a cup. Good. Right here, the second derivative changes from positive to negative. I actually got that one right. So this would also be an inflection value, okay? But it's also a PIV before it's an IV. Why is that? Well, because the sign of the second derivative changes. Now, what would be the value of the second derivative there? It has to be dne, right? The function's defined there, but is the first derivative defined there? No. So if the first derivative is not defined at P, the second derivative will not. Okay, because you can't even, there's no way to find where something that doesn't exist exists further down the road. It's out. So once you hit dne, subsequent derivatives are dne also. So that, because it's also an inflection value, then when we find our candidates, that's going to show up on our radar as a PIV. Okay, same thing over here. Notice that the second derivative is positive on the left and positive on the right. Is that actually an inflection value? No, the concavity didn't change signs. But does it show up as a possible inflection value? Well, let's see. What is the value of f double prime of p? It would also be dne, right? So just like we want to know where the first derivative is possibly undefined, define cusps and vertical tangents, we want to know where the second derivative is undefined because it's a possible inflection value. But notice not every PIV, possible inflection value, ends up being an IV, just like not every critical value ends up being local max or min. Okay, did this end up being an inflection point at x equals p? We didn't write it on here, but let's see if I can recover y'all's trust here. On the left, it's part of a frown, so the second derivative is negative on the left, and on the right, it's part of a smile, so the second derivative is positive. So at x equals p, the sign of f double prime changes from negative to positive. Is x equals p then an inflection point? No. Okay. Why? Because x equals p is not in the domain of f, right? F of p equals dne. So remember, just like a critical value, it has to be in the domain. So would it show up in a number line chart if we were trying to determine intervals of concave up and down? Absolutely. Okay, just like if we're trying to determine where is the graph increasing and decreasing, we put discontinuities in there. And because curvature, like slopes, can change signs at a discontinuity that's not in the domain, they do make their way into any number line chart. So what we're going to be doing then is everything with the first derivative in the first derivative number line chart, we're going to be doing again for the second derivative. Okay. So here's the theorem. First of all, the graph of a function can only change its concavity at a PIV, that is a value in the domain where the second derivative is 0 and defined, or at a discontinuity, right? We just saw that. An inflection value then can only occur at a PIV, not at a vertical asymptote. But not every PIV, of course, as we just saw, is an inflection value. Good. So what we're going to start with is testing for intervals of concavity. Like in the previous section, we tested to see where the graph was increasing or decreasing. We want to know where is the graph part of a smile or part of a frown. All right, so here's how we're going to test those intervals. We're going to find any discontinuities of the function. They're going to make their way into the chart. We're going to identify any PIVs that are in the domain of the function by, again, seeing where the second derivative is 0 undefined. We're going to make our number line chart, testing in between those values. And wherever the second derivative is positive, the graph of f is concave up on that interval. And wherever the second derivative is negative, f is concave down on that interval. Okay? All right, so let's start with a graph before we get to the equation. Here's the graph of the function. It's defined everywhere on the interval from a to k. Now notice that's a closed interval. So from a to k. So even though there's nothing on the end there, we'll assume that it's continuous at the left endpoint, and we'll assume that it's continuous at the right endpoint. Okay. Give the possible inflection values, PIVs, okay? Is A PIV? Well, what's the definition of a PIV? First of all, is it in the domain of the function? Yes. Good. Is the second derivative defined there? No, because the first derivative is not defined there, right? Because it's an endpoint. So if the first derivative doesn't exist there, the second derivative doesn't. It is a PIV, okay? But just like a local max or min can occur at an endpoint, neither can an inflection point, right? Because we don't know what the concavity is to the other side. But it is a PIV. So you got to read carefully. Is the question asking you for possible inflection values or just inflection values? All right, what about B? Is it a PIV? Yes, okay. And we know because it's an actual inflection point, right? Because the graph to the left is concave down and to the right it's concave up. So for sure, if it's an inflection point, it's a possible inflection point. What about at C? Yeah. The graph goes from concave up to concave down, so the second derivative is equal to 0 there. It's probably worth doing that. F double prime of B equals 0. F double prime of C equals 0. What about D? Is it a possible inflection value? Yeah, good. It goes from concave down to concave up. What's the value of the second derivative there? Does not exist. Good. The first derivative doesn't exist there. It's a cusp. Therefore, the second derivative does not. But it is a PIV. All right, what about at E? PIV, yes or no? Yes, it is. Good. And you can tell just because there's a cusp. Anywhere there's a cusp, it's not only going to be a critical value, it's a possible inflection value. Okay, so E is in there as our list of candidates. What about H? Is it a PIV, a possible inflection value? Or possible, prospective, plausible, potential inflection value? It is, right? It's in the domain. There's a dot there. And what's the value of the first derivative there? D and E. Remember, any discontinuity, the derivative fails to exist, and therefore, the second derivative also fails to exist there. And because it's in the domain, it's another possible inflection value. Okay, so there's H. And then what about K? Yeah, same reason the left endpoint. So every single value that I had listed there, A, B, C, D, E, H, K. I didn't use F because the function's name is F. And I didn't use G because we use that as well. H, I is kind of a dumb one. So I jumped to K. Okay, anyway, at each PIV then determine if F actually has an inflection value justify. Okay, so what about at A? No. So we'll say not at A, comma, since X equals A, that's all you have to say, since X equals A is the left endpoint. We don't know what the concavity is to the other side. What about at B? Yes, right? Yes. At B, at X equals B, comma, since F double prime changes, remember we always want to get in the habit in talking about a sign change. So since F double prime changes from what to what there? It's negative to positive. Good. So instead of saying F changes from concave down to concave up, we're going to say F double prime changes from negative to positive, not in France, but at X equals K. So pretty much the same type of, or at X equals B, sorry. The same justification that we did for the first derivative test. At C, concave up to concave down, so yes. At X equals C, comma, since F double prime changes, this time from positive to negative. Not in France, but at X equals C. All right, what about D? Concave down on the left, concave up on the right? Yes. Now, because it changes in the same way that B does, here's what you could do. If you're going to write a statement, you could just throw it in there at X equals B, comma, D. Since F double prime changes from negative to positive, at X equals B, comma, D. All right? You're typically not going to have to do it for all the points across the board. But if you could do it for every single one of them, you could do it for any one of them. What about at E? It's a PIV, but is it an actual IV? Nope. Okay. So not and it's different from the first one, not at x equals d, comma, since f double prime is positive on either side of x equals d. So kind of the same sentence we would write if we had a critical value that was neither a local max nor a local min. We're saying immediately to the left and immediately to the right, the second derivative is positive. And we've already declared them as PIVs up above. All right, what about at, yeah, that was it. Yeah, I'm sorry, I did that wrong. We never wrote the sentence, so I messed myself up there. We're at E, thank you, and now we're looking at H. All right, so what about H? Inflection value, yes or no? It is, right? The graph is concave up, part of a smile to the left, concave down to the right. So the second derivative changes from positive to negative. Positive to negative, we've already said that once, so we could throw that in there with the next one. At x equals c comma h, since f double prime changes from positive to negative at c comma h. There you go. And then finally the last one, at x equals k, you could say no, not at x equals a, or x equals k, since x equals a is left endpoint, and x equals k is the right endpoint. So we look for a sign change in the second derivative. Okay, list the open intervals on which the function f is concave up, concave down, or constant. So we could just say f is, we'll say dot, 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 cc up. Okay, you can abbreviate concave up, concave down as cc up, cc down between now and the day of the AP exam. On the day of the AP exam, you write concave. Okay, so concave up, it would be from, let's see, B to C. And again, there's no justification here. B union, or B comma C union, where would be the next one? D to E? Oh yeah, it would be from D to H, or D to E, then E to H. What you're saying is we can combine those and say from D to H. Would you all agree? If we go from D to H, we're saying that the graph of F is concave up at E. Can we say that? Does the concavity exist at E? No. So just like we can't say that the slope at E is positive or negative because the derivative doesn't exist there, you can't say the graph of F is concave up or concave down if the second derivative doesn't exist there. So you would have to be careful. You would have to step over it and list it as two separate intervals, okay? But that was nice. Normally, if it's a singularity, we can go right through it, but it has to exist there. All right, good point of discussion. And then concave up, it looks like it's it, right? And then CC down like frown on all the other intervals, right? Which it comes in concave down, so A to B, union C to D, and then H to K, union H to K. All right. So that was just to kind of practice our sentences. And so just like with the first derivative, if we want to know if it's a local max or min, we look for a sign change in F prime, but we can also determine where it's increasing, decreasing. Same thing with second derivative. We can determine if there's an actual inflection value. We make no distinction, though, between the types of inflection values, the ones that change from negative to positive or positive to negative. For first derivative stuff, that's the difference between a local max and local min, right? But we make no distinction between inflection values. We don't call it like a local max inflection value and a local min inflection value. We just call it inflection value, but we still have to say how it changes. And then we can use those numbers then to determine whether the graph is concave up or down, okay? All right. So just like the first derivative, the number line chart can help you organize your second derivative information. So important things to reiterate, which it's kind of funny. Iterate by itself means to repeat. So reiterate is re-repeating, right? Re-repeating. Not every PIV is an IV. Not every PIV is an IV. Okay, but we could say this. A PIV is to an IV as, and I think we've used this notation before, the analogy, as a critical value CV is to a local max or min. Okay? The vocabulary just isn't as great for the second derivative. Okay? A PIV is to an IV as a CV is to a local max or min. Concavity can change at a discontinuity, such as a vertical asymptote, but if it's not in the domain, it won't be an inflection point if it's a vertical asymptote. To find your possible inflection values, again, make sure they're in the domain, see where the second derivative is 0 undefined, and then make a number line chart that has all of your PIVs and any discontinuity, and then test the intervals. Okay, let's try it out. See if we can get one in before lunch. For each of the following functions, find the PIVs, then the inflection values with justification, and then determine the open intervals of concavity. All right, so 3 plus sine of x from 0 to 2 pi. We could probably sketch this one really, really quickly and answer all the questions without actually doing a lick of calculus. But let's not. Let's do the calculus, and then we'll compare it to what we know after the fact. All right, so first things first, what's the domain of this function? All real numbers, good. So now we need to get to the second derivative, which means we have to go through the first derivative. So y prime is going to be cosine of x, and y double prime is negative sine of x. So there's your fully intact second derivative. Is that ever undefined? No. So remember, we want to consider that. You don't have to physically write it, y double prime equals d and e, but you always want to consider it. It's never undefined. So if you only want to know where it's equal to 0, you could just set it equal to 0. And remember, that always gets a check when you show the equation you're solving. Now, if you multiply both sides by -1, you got to be real careful because it goes away on both sides. But is this still the second derivative? It's not. So I would not recommend you do that because it can mess you up when you come back in your number line chart. So just leave the negative intact and maybe box it. But where is sine going to equal 0 between 0 and 2 pi? 0 and pi. And would we include 2 pi the way it's written right here? Yeah, we would because it's a bracket. Now 0 and 2 pi are both endpoints, right? So on this closed interval, we're not going to look to the left and right of 0 and 2 pi respectively. So the only open interval PIV is pi. One last check. Are there any discontinuities? Any vertical asymptotes? No. So those are the only numbers that go on my number line chart. So here we go. X and y double prime, or f double prime. And we've got pi essentially. Because remember, we're looking on the closed interval from 0 to 2 pi. So we don't look to the left of 0 or to the right of 2 pi. So now we just pick some numbers between 0 and pi, like, I don't know, pi halves. That was the flash. And 3 pi halves. Yeah, interesting. All right, let's get the sine. If our eyes are still working. We plug it back into the second derivative. So what is negative sine of pi halves? Well, sine of pi halves is positive 1 times the negative makes it negative. Yeah. Sine of 3 pi halves is negative 1 times the negative makes it positive. So notice if you solve by multiplying both sides by negative and accidentally plugged into the wrong thing, you're going to get the exact opposite of what you're supposed to get. All right. So from here, we pretty much have all that we need. Is x equal pi then an inflection value? Yes. And you would say y has an inflection value at x equals pi, comma, since y double prime changes from negative to positive at x equals pi, just like you would if it were a local min. Intervals of concave down, y is concave down from 0 to pi, open interval, and y is concave up from pi to 2 pi. That pretty much answers that entire question. Okay, so we didn't have time to write all that down, but it's lunchtime, and we'll pick up, and we'll write the sentences after that one. So on part B, we'll write the sentences. All right, so have a fantastic, super duper awesome, wonderful lunch.